All right, we are back. So, during this video, it is my intent to explore some non-examples of uniform continuity and also a very large family of examples of uniform continuity. So let's go ahead and begin. So in the previous video, I kind of asserted that f of x equal to 1 over x and g of x equal to sine of x are not uniformly continuous. The arguments that appeared above don't actually prove this. Failure to produce a delta that's independent of your choice of A is not the same as proving that no such choice exists. If we want to prove that a function is not uniformly continuous, we need a proof that it's not uniformly continuous. We can't just have a proof that it is continuous that fails to be a proof of uniform continuity. So let's go ahead and pull that off. So let's do that. So claim 3.8.5, f of x equal to 1 over x is not uniformly continuous at the interval from 0 to infinity. And let's, to the side, figure out what it is that we actually need to prove. So let's write that down. So what do we want to show? We want to show not g of x equal to 1 over x is uniformly continuous on 0 to infinity. And let's explore what that means. So let's remember the definition of uniform continuity. So we want to show not, I'll use the triple bar, this is an equivalent statement too. We want to show not for all epsilon greater than 0, there exists a single choice of delta greater than 0, allowed to depend on epsilon, such that for every pair of inputs, it looks like here I'll use x and a, but it doesn't matter what the variable name is. For all x, comma a in 0 to infinity, if absolute value of x minus a is less than delta, then absolute value of 1 over x minus 1 over a is less than epsilon. And well, at this point, we're probably getting pretty good at negating logical expressions, so let's negate that logical expression. So we negate a universal to get an existential, right? If it is not the fact that for every epsilon bigger than 0, a thing is true, that means there must exist a counterexample. There must exist an epsilon bigger than 0, so that all the stuff after that is false. So there exists an epsilon greater than 0, such that there exists a delta. So there does not exist a delta such that the stuff after this happens. So that means that for every delta, the stuff after that doesn't happen. For every delta greater than 0, there exists a pair x and a in the interval from 0 to infinity, such that when you negate an if, then you see that you want to show there exists something where the hypothesis happens, but the conclusion does not happen, because then the implication will be false, such that absolute value of x minus a is less than delta, and absolute value 1 over x minus 1 over a greater than or equal to epsilon. So there's what we want to show. So let's put that in the actual proof now. By negating the definition of uniform continuity, we see that we need to prove that there exists an epsilon bigger than 0, such that no matter what delta we pick, why won't it zoom in correctly? There exists an x and an a in 0 to infinity, such that absolute value of x minus a is less than delta, and absolute value of 1 over x minus 1 over a bigger than or equal to epsilon. And in order to motivate the proof, let's actually go to the side and, oh, I called it g when it should have been f. That's an error on my part. So let's look at a graph and try to figure out how the proof should go. So let's look at a graph of this function. So the graph of the function looks something like this. And if we look at this, what do we want to find? So let's just look over here at the conclusion. I want to find a pair of inputs which are close to each other, for which the outputs are not close to each other. And well, we kind of see over here how to do that. So there are two outputs that are kind of far apart, but the corresponding inputs are super close to each other. So it looks like I just want to take inputs that are getting super close to 0. Nice. And that agrees with the fact that the place where uniform continuity failed was close to 0. In the previous proof where that failed to prove uniform continuity. So let's do that. Looking at the graph over here, we could make this gap be as big as we wanted, right? So we don't need like a full all epsilon, so let's just take a gap of 1. I bet you could take any gap you wanted. In fact, that might be an interesting example to make sure you understand what's going on. So let's take epsilon to be 1. You can take it to be 1/2 as you do it on your own. You can take it to be 2 or 5, I think. Consider any delta bigger than 0. Right, so because we want to show there exists an epsilon bigger than 0. So we need to come up with a choice of epsilon, and that epsilon can't depend on anything. Next, we should consider any delta bigger than 0. Now we have to come up with a choice of x and a in the interval from 0 to infinity, such that the absolute value of x minus a is less than delta, and the absolute value of 1 over x minus 1 over a is bigger than or equal to epsilon, which we took to be 1. Maybe you took it to be 2. That would be fine if you did. So let's try to come up with a pair. Now it says here you'll need to fill in the choice of epsilon. Let's figure out the choice of x together. So let's see. So over here we could have taken two inputs really close. So one way of doing that is taking an input that's really close to 0 and then doubling it. That's still really close to 0. So let's take x to be something that we get to choose. We'll get to choose what x is, and a to be 2 times that x value. Let's see, then I'll need 2 things, and let's go off to the side and do more scratch walk. These are the 2 requirements we need. We need absolute value of x minus a to be less than delta. So let's explore what that is. Absolute value of x minus a. A is 2 times x. So that will be absolute value of x minus 2x. Well, you stare at that for a second, you see that that's just absolute value of x. So I just need absolute value of x to be something that's less than delta. That's what I will need. The other condition that I'll need is absolute value of f of x minus f of a. I need that to be bigger than or equal to epsilon. Well, let's explore that. So f of x is 1 over x minus 1 over a. I need that to be bigger than or equal to 1. And so this is just going to be scratch walk, so I'll manipulate by hand, and then we'll write out the details once we know what the details should be. So that'll be a minus, well, goodness. You know what? I know what a is. A is 2 times x. So this will be 1 over x minus 1 over 2x bigger than or equal to 1. Oh, well, that simplifies, right? That's just 1 over 2x bigger than or equal to 1. So let's, I guess, solve that for x. Everything's positive, so I can erase the absolute value bars. Right, x by assumption is bigger than or equal to 0. Let's move that to the other side. 1 is bigger than or equal to 2x. 1/2 is bigger than or equal to x. So it looks like I need two things. I need x to be less than delta. Oh, that inequality got written the wrong way around. And I need x to be less than or equal to 1/2. So I know how to get both of those results. Let's take x to be the min between 1/2 and 1 over, nope, delta over 2, 1/2 delta. Nice. So now, with that choice of x and a, let's just explore everything. So that means that the absolute value of x minus a is the absolute value of x minus 2x is equal to the absolute value of x. Well, yeah, this will be fine. So let's do this walk right here. So let's see, by our choice of x, since x is the min between 1/2 and 1/2 delta, what do we get? We get absolute value of x minus a. We've just checked that that's the same thing as absolute x. And I need it to be less than or equal to delta. So which of these two things results in it being less than or equal to less than delta? This does. Less than or equal to 1/2 delta, which in turn is less than delta. Cool. So we get that result. Now I need the absolute value of f of x minus f of a to be bigger than or equal to epsilon, which, remember, is just 1. Great. Well, let's do that. So absolute value of f of x minus f of a, that's the same thing as 1 over x minus 1 over a equals absolute value of a, well, see, I'm going and simplifying it when instead what I should do is just plug in the fact that I know what a is. So that's the same thing as 1 over x minus 1 over 2x. That's exactly 1 over 2x. And well, let's see, because that's bigger than or equal to 1 over 2 times 1/2, which is 1, since x is less than or equal to 1/2. So let's just go ahead and summarize what we've done. So we started by picking a particular choice of epsilon. So thus, there exists an epsilon greater than 0, such that we considered any delta, such that no matter what delta greater than 0 we pick, there exists some x and a in 0 to infinity. To be specific, they were x equal to 1/2, the min between 1/2 and 1/2 delta, and a equal to double that. So I guess we could rewrite that as the min between 1 and delta. Yeah. There exists an x and a in there such that absolute value of x minus a is less than delta, and, or maybe you would want to say but, absolute value of f of x minus f of a greater than or equal to epsilon. Therefore, f of x equal to 1 over x is not uniformly continuous on 0 to infinity. Groovy. So let's do one more. So I'll encourage you at this point to stop the video and come up with your own proof for g of x equal to sine of x. Okay, good. You did that. Let's come back and talk through a proof. So I'm going to start by going off to the side and coming up with a scratch walk setup. So let's look at the graph of g of x. So the graph of y equal to the sine of x, that graph looks something like this. So the game is, if you want to show that a function is not uniformly continuous, you want to show that there exist two inputs which are really, really close to each other, for which the outputs are not really, really close to each other. And, well, there are two inputs that are pretty close to each other, just opposite sides of the origin. The corresponding outputs are 1 and -1, respectively. That's far apart from each other. Nice. So I think that actually is the choice we'll use. So this distance between them is 2. So they definitely are not within a distance of 1 of each other. So again, I'll take epsilon to be 1. I'll consider any delta bigger than 0. I'll let x be something positive and a be, well, I guess negative x is what that picture suggests. Then, absolute value of x minus a is the absolute value of x minus negative x. But I know what that is. That's 2 times the absolute value of x. So, I will need that. So let's go off to the side again. We will need 2 times absolute x to be less than delta. So I can solve that easily enough for x. It looks like I'll need absolute value of x to be less than delta. And right, I get to pick what x is. And motivated by this picture, it looks like I want 2 numbers, one of them positive, the other one negative. X may as well be the positive one of the 2. That'll make this easier at least. So maybe I'll need delta over 2. Christ, did I at least say delta over 2? Sorry, I'm upset because I went back and re-recorded about 2 minutes of content because I only noticed that error. Anyway, delta over 2. So 0 less than x less than delta over 2. Well, what's a number between 0 and delta over 2? Well, how about delta over 4? Let's see if that works. So let's take x to be delta over 4 and a to be negative x. So let's just write that down. So that'll be 2 times delta over 4. Well, that's delta over 2. Yeah, that's less than delta. So we're happy. On the other hand, let's put a period at that. That's the end of a sentence. On the other hand, absolute value of f of x minus f of a, let's write down what that is. So g of x minus g of a. So let's write down both what x is and what a is and what g, the function g is. So that's the sine is spelled with an I, of delta over 4 minus the sine of negative delta over 4, which is equal to, well, delta's positive. A positive number has sine plus 1. The sine of negative delta over 4 is negative 1. And let's even put a break here, because delta over 4 is bigger than 0. And now we can just explore that. That's equal to negative 1 minus 1 is 2. Absolute value of that is 2. That's bigger than 1, which is epsilon. So I didn't include space for this, but let's, just for the sake of getting good practice in, let's include this concluding sentence. So the concluding sentence there is, so write what we've proved. Thus, there exists a choice of epsilon bigger than 0, and maybe we can even be specific in our conclusion. Namely, epsilon equal to 1, such that for every delta bigger than 0, because we considered any delta bigger than 0 in our proof, there exists some x and a in R minus 0. And maybe we can even be specific, namely x equal to delta over 4, a equal to negative x, such that absolute value of x minus a is less than delta, and absolute value of g of x minus g of a is greater than or equal to epsilon. Therefore, this function, g of x, is not uniformly continuous on R minus singleton 0. Cool. So that's two examples of things not uniformly continuous. I think I will now go through two examples of things that are uniformly continuous. So here's one. Let's let f from R to R be given by f of x equal to 3x plus 10. I claim that f is uniformly continuous on all of R. So again, I'm going to make considerable use of the very wide margins, infinite margins, that I have because I'm walking on a tablet. Well, so let's see. I'll want to show for every epsilon bigger than 0, there exists a delta bigger than 0 such that for all x and a in the real number line, if absolute value of x minus a is less than delta, then absolute value of, well, I have a formula for this function, right? 3x plus 10. 3x plus 10 minus 3a plus 10 is less than epsilon. And maybe we can even do the scratch walk and come up with the proof right here. So let's see. Maybe you would want to distribute the negative sign, but this is just scratch walk. The 10s will cancel. So this will become absolute 3x minus 3a. That is 3 absolute x minus a. I get to assume absolute value of x minus a is less than delta, so that's less than 3 delta. Oh, cool. So I can set that equal to epsilon, and I'll get delta equal to epsilon over 3. And let's just do a quick check. That formula for delta, it depends on epsilon. That's fine. That's allowed. It does not depend on x, and it does not depend on a. Good. That is an okay choice of delta. So let's use that choice of delta. Consider any epsilon bigger than 0. We will let delta be epsilon over 3. Consider any x and a in the real number line. Assume that the absolute value of x minus a is less than delta. Then, well, you can fill in this on your own. So I encourage you to pause the video, do that. I'll do it too, but then you can like pretend that you're watching, put the video on like 10x speed until I'm done. I tend to talk slow, I think. Absolute value of f of x minus f of a is equal to absolute value. Definition of f of x is, why am I still writing in yellow? 3x plus 10 parentheses, minus 3a plus 10, parentheses because they're important, is equal to 3 times x minus a is equal to 3x minus a is less than 3 delta, which is equal to epsilon by our choice of delta. Cool. So, summarizing what we've done, we started by considering any epsilon bigger than 0. So this, we proved something for every epsilon bigger than 0. We wrote down a choice of a delta. So there is some delta, such that we considered any x and a in R. So that for all x and a in R, if the absolute value of x minus a is less than delta, we assumed absolute value of x minus a is less than delta, and proved that absolute value of f of x minus f of a is less than epsilon. So this function is uniformly continuous. So maybe you could even imagine that you could generalize this, right? Any linear function is probably uniformly continuous. Y equal to mx plus b. I bet you could even come up with the choice of delta right now. I believe that's one of the homework problems. If it's not, it should be. Probably by the time you get the video, I'll have added it. Cool, so let's keep on trucking. So let's consider this function. Let's let f be defined from -1 to infinity. Let's let it be given by f of x equal to 1 over x. I claim that this function will be uniformly continuous on the closed interval from 1 to infinity. And maybe we'll motivate why that should be true. So Let's look at how our proof of non-uniform continuity of 1 over x went. The inputs we used were really close to 0. So let's just avoid inputs that are close to 0. All right, so let's consider any epsilon bigger than 0. We'll let delta be something that we choose. We'll consider any x and a in the interval from 1 to infinity. And let's see what we can do with absolute value of 1 over x minus 1 over a. So here's some scratch walk. Let's see, 1 over x minus 1 over a, absolute value bars. We've done this enough times that you already know how that's going to go. So what do I get to assume about x and a? I get to assume that they are in the interval from 1 to infinity. In particular, they're both positive. This is just scratch walk, so that's okay to write things that are kind of ugly. Well, let's see. I do know that this will be less than delta over x times a, but if I use that and that alone, then my choice of delta will depend on epsilon and x and a. That's really, really bad. Even in a proof of continuity, delta can't depend on a. Our choice of delta here would depend on everything. So that's no good. Well, wait, I know more than just x and a are positive. Let's use that fact that x is greater than or equal to 1, and that a is greater than or equal to 1. So this thing in the denominator is something bigger than 1 times something bigger than 1. Something bigger than 1 times something bigger than 1 is also bigger than 1. So this is, this denominator is bigger than or equal to 1. That means that this quantity is less than or equal to delta over 1, also known as delta. Well, do you think I could use that to come up with a choice of delta so that delta is equal to epsilon? Could you solve that for delta? Yeah, of course you could. It's already done, right? So let's use that. Consider any epsilon bigger than 0. Let's let delta be equal to epsilon. Consider any x and a in the closed interval from 1 to infinity. Assume that the absolute value of x minus a is less than delta. Then, well, let's see what we get. Absolute value of f of x minus f of a is equal to the absolute value of 1 over x minus 1 over a is equal to absolute value of a minus x over x times a. Let's put those absolute value bars in. And this in turn, let's use the fact that that denominator is bigger than or equal to 1. So that's less than or equal to absolute value of a minus x over 1. Since x is greater than or equal to 1 and a is greater than or equal to 1. Cool. But that x minus a is less, absolute value of a minus x is the same thing as absolute value of x minus a. That is less than delta, which is equal to epsilon, since absolute value of x minus a is less than delta, which is equal to epsilon by assumption. Oh, nice. So that was actually pretty easy. Thus, for every epsilon bigger than 0, there exists a single choice of delta depending only on epsilon, not on the input, such that for any two inputs, if those two inputs are within a delta, then the resulting outputs are within an epsilon. This function is uniformly continuous. That is a result of a bad copy pasta. So I'm going to stop there with this video. Hopefully going through those examples was helpful. I want to give two results which will tell you that there are lots and lots of uniformly continuous functions. So here's a theorem which says that continuity on a closed bounded interval implies uniform continuity. Let a be less than b, and f from a comma b to r be continuous. Then f is uniformly continuous on a comma b. Nice. So I won't prove that in this video. It's been about 30 minutes. I think that's a good length for this video to be. I'll go ahead and stop. There will be a few more videos coming out of this. The next two will be pretty short. Groovy. Take it easy. I'll talk to you soon.